Here's your, say hi, Max. Okay, go.
Okay. Think about the world 40 years from now. I'll be almost 60 years old. Maybe you'll be retired or have grandkids, or live in a big house in the country with a big truck. But according to the International Energy Agency, you probably won't want to drive that truck very much. Their estimates place the exhaustion of current proven oil reserves occurring sometime between 2040 and 2060. And while that doesn't mean that we'll be completely out of gas, it does mean that its use could get much more regulated and it could become much more expensive. The future of energy impacts everyone, whether you'll have a job in the energy industry or just be using the energy that's produced. So fortunately for all of us, nuclear fusion is poised to help solve our energy issues, and scientists are working on collaborative projects that could have it ready by 2050. I've been interested in nuclear fusion for a while, and read extensively online and in my high school library for this speech. So today I'm going to first tell you about general fusion information, then I'll move on to more specific details about the fuels and conditions necessary for nuclear fusion. Finally, I'll discuss current progress in developing nuclear fusion power plants and tentative timelines for its completion. Nuclear fusion is very different from nuclear fission and comes with its own unique challenges. Both of these processes are called nuclear because they produce energy through the interaction of atomic nuclei. In fission, the atom is being split. You start with one large one and split it into two smaller ones. And in fusion, two smaller atoms are joined to form a larger one. Nuclear fusion has often been called the power of the stars, and this is cited as proof of its immense power and sustainability. Edmund Sienikowski, in the congressional hearing, The Next Generation of Fusion Research, said that Einstein's famous equation E equals mc squared is at the heart of nuclear fusion. E equals mc squared explains the relationship between energy and mass. Basically, it's saying that the energy contained in matter is equal to the mass of that matter multiplied by the speed of light squared. Alex Bradshaw and Thomas Hamaker explained the relationship between this equation and fusion in their 2001 paper titled Fusion as a Power Source, saying that energy is gained in nuclear fusion and at the same time mass is lost. The efficiency of this mass-to-energy conversion is 1 million times greater than that of burning fossil fuels. So for example, this truck, if it could actually run, might be able to travel about 40 meters with an ounce of gasoline. It's pretty small, so I think that's reasonable, and that's about the height of a really tall tree. If it was powered with nuclear fusion, however, and you gave it an ounce of hydrogen, it could travel 1 million times as far, so 40 million meters. That's about the distance around the entire Earth. The two fuels most likely to be used in nuclear fusion are deuterium and tritium. The ITER organization, which is currently developing the world's largest fusion reactor at 10 times larger than any currently operating, says that deuterium-tritium fusion produces the highest energy at the lowest temperatures. Deuterium and tritium are both isotopes of hydrogen, which means that they have the same number of protons as hydrogen, but different numbers of neutrons. And they're relatively easily obtained. About 1 in 6,000 naturally occurring hydrogen atoms is deuterium, and tritium can be produced with lithium and waste products from fusion. Dr. Ricardo Betti, in the same congressional hearing, The Next Generation of Fusion Research, said that the fuel for fusion is basically unlimited. The conditions under which fusion occur, however, are extraordinary. In attempting to build a fusion power plant, scientists are essentially building a miniature star here on Earth, and this comes with two major difficulties. The first is heat. William P. Alice, in his 1960 book, Nuclear Fusion, said that the ideal temperature for deuterium-tritium fusion is 564 million degrees Fahrenheit. The ITER organization said that current reactors regularly exceed 180 million degrees Fahrenheit. That's 5 times hotter than the sun's core. The second major difficulty is confinement. Stars have immense gravitational force that holds everything in place, and this isn't available to us on Earth, so scientists must come up with other ways for this confinement to happen. The heat and density both work together to overcome the force that it repels atomic nuclei from each other naturally. Heat gives them enough energy to collide randomly and react, and the density caused by confinement makes these random collisions more common. So I realize that I just said a lot, but if you forget everything else, just remember these 3 main points. Fusion can create a lot of energy, its fuels are plentiful, but it requires lots of heat and pressure for it to occur. So now that you have a more comprehensive understanding of nuclear fusion, I'll move on to discussing the current state of fusion research and into creating power plants. When I started researching this, I was surprised at how advanced fusion research is. There are many fusion reactors all over the world currently operating. These plants, however, only dissipate the power that they create. They don't contribute any electricity to the grid. Even the next generation of reactors, like ITER, won't contribute any electricity. And it will likely be decades before power companies have enough confidence to build their own reactors. Scientists are also having difficulty sustaining reactions. Heating plasma takes more energy than it currently gives, and methods of maintaining electrical charges in plasma necessary for its confinement can currently operate for only 1 to 2 hours at the very most. Commercial widespread fusion likely won't be seen until sometime between 2040 and 2060. So I've introduced you to some basics of nuclear fusion and discussed some more detailed specifics. I've also discussed a timeline for its possible completion, so I'll conclude with this thought. Fusion is a complex process, and its development is slow, but collaborative projects are making it a real possibility. Maybe in 40 years from now, we won't be so bad after all. With fusion, a future of clean, endless energy could be ours to keep.